Hello everyone, today I'm going to present our work, Adaptive Planner Parameter Learning from Interventions. This work is accomplished by me and my great collaborators, Xuesu Xiao, Bo Liu, Gertrude Wonnell, and Peter Stone. We are from Learning Agents Research Group at the University of Texas at Austin. So first, let's look at the motivation of our work. So we hope to deploy navigation system into different environments. However, if we are going to use some classical navigation system, for example, optimization-based or sampling-based, and whenever we deploy to a new environment, we may need to adapt its parameters. For example, we may need to reduce the maximum speed in a more cluttered environment. Otherwise, if you keep using the same parameters, it will produce suboptimal behaviors or even fails. However, it's not very easy to tune those parameters and it requires expert knowledge. However, for human, even if he's not an expert, it's easy to provide some interventions. So for example, here, when the robot struggles and cannot find the feasible motions, one of the authors will set it back and give it a short demonstration via teleoperation. And similar here, when the robot drives too slowly in this open space. So maybe we can use these interventions collected to tune the parameters. So here we first review some related works. Machine learning has achieved a lot of progress in navigation, and they are at different granularities. For example, some end-to-end learning work replace the whole navigation stack. And also there are some work just replace subsystems. For example, just replace the global planner or the local planner. There are also works focusing on small components in the subsystem. For example, replacing the cost function or cost map, or to tune the planner parameters. And this is the focus of our method, to tune the parameters for the local planner. And another important background is our series of work, APPLI, Adaptive Planner Parameter Learning. So we all know the navigation system, it will take the sensor data and using its own algorithm with some parameters and generates the model commands. So the goal of the APPLI framework is to use human interactions of different modalities to tune the parameters for the navigation system. So one of our previous work is APPLI-D that uses human demonstration, and the parallel work is APPLI-R using reinforcement learning, which is also accepted to ICRA, and you can find it in the next presentation. Okay, go back to our work. So what's the contribution compared to previous work or parallel work? So here we use a few interventions rather than a full demonstration to just focus on the challenging scenario for the robots. Also, we use a confidence context classifier to generalize better to on-scene environment. So this will introduce in next few slides. And also, pay attention to the interventions we collected. There are two categories. One is the failure case, type A, when the robot fails to find a feasible motion, or type B, where the robot shows suboptimal behaviors, for example, driving too slowly in this open space. So there are three steps in the APPLI framework. So first, we collect a bunch of interventions from human supervisor, where each intervention consists of a series of observation-action pairs. And also, we consider different human concentration or expertise level here. For example, when the human are not very focused, or they are not expert with this robot. In this case, they may not recognize suboptimal behaviors, and as a result, won't provide corresponding type B interventions. And in that case, we will only use type A interventions. The second step is to apply black box optimization method to find navigation system parameters for each intervention. And the third step is during deployment, whenever we see a new scenario, we need to know whether it's at scenarios where we have collected interventions. And if that's the case, we need to decide which intervention scenario it matches. So in that case, we need the context classifier, and we also need the confidence measures. So the technique we use here is evidential deep learning, where you can find detail in this paper. So let's look how it works. So whenever we decide the current scenarios from the sensor data, we will not only predict the probability for each context we have collected, but we will also have a confidence measure. So when this confidence measure is very high, we are pretty confident and we can trust our prediction. And in that case, we will just choose the context that has highest prediction probability, context 1 in this case. And as a result, we use the parameter theta1 learned from this context 1. However, when the confidence is low, in that case, even we may have higher prediction probability, we won't trust that, and instead we use the default standard parameters, theta bar, because this parameter is tuned to be good everywhere. And in that case, it should generalize better than those specialized parameters. Next, we evaluate APPLI using both real and simulated experiments. In real experiments, we use a Gecko robot, and its observation comes from this Velodyne data. And one of the authors provide interventions through teleoperations. In the training environment, we collected 4 interventions, 2 type A and 2 type B. And we also tested in this on-scene environment. In this training environment, we compare APPLI with different number of interventions and even full demonstration, and we also compare it against the planner with default parameters. So if we compare the traversal time across 5 trials, we can see APPLI using both A and B interventions achieve best performance, and it's much faster than the default parameters. And in this on-scene environment, we can see similar performance. APPLI with A and B interventions perform the best. However, we can see APPLI with A and B is even better than APPLI or learning from 4 demonstrations. So why is that the case? Because the actual demonstration collected in the green here are where the robot already performs pretty well. And in that case, the human demonstration are unnecessary and they may be suboptimal. And in that case, they will harm the performance of APPLI. So here we show some qualitative results. So you can find here the default parameter still struggle at this place, while other method already drive through smoothly. And they also drive pretty fast in this open space, while the default planner drives very slowly. So due to time limit, we cannot show the full video here as well as the video for on-scene environment, but you can find them and watch them on our website. So next, to further test the generalizability of APPLI with the 4 real-world interventions collected we just have seen, we test it in this barn dataset. So it's a simulated dataset with simulation trials of different difficulty levels. So we run 25K simulation trials in this barn dataset. And we compare again APPLI with different number of interventions, and also with or without this confidence measure in the context predictor. And again, we compare with the default parameters. So first, let's look at here. We can see that if APPLI only use type A interventions and without confidence measure in the context predictor. So it performs much worse and even worse than this default parameter. However, if it uses confidence, it will be slightly better than this default standard. However, if we see using context confidence measure or not for 4 interventions or even the full demonstration, it seems the confidence measure doesn't differ much or doesn't make a difference. So what if we can learn? So it seems that the confidence measure is very important when the collected interventions are not sufficiently generalizable. So when it only has 2 interventions, we cannot expect it to work for every scenario in this simulated environment. However, when it has 4 or even 4 demonstrations, it can generalize much better. So in that case, using confidence measure or not doesn't differ much. And also, similar to what we have seen in the real experiment. So we can see using full demonstration here, its performance is worse than using only A and B interventions. This again suggests unnecessary demonstration may be suboptimal and harm the performance. Cool. So after seeing our method, 2 important future directions are listed here. So the first one is, no matter whether it's APPLI or APPLI, which use demonstration or interventions, we require the human to control the robot. However, can we use some interaction modalities that are easier to collect? For example, evaluative feedback that doesn't require human to control the robot. The second direction is, in the APPLI framework, we have a lot of methods. Can we integrate them and combine them to further improve the performance of navigation system and maybe form some cycle of learning? That's all my presentation. Thanks for listening. And you can also access our paper here by scanning this QR code.